Okay, so we're going to talk about a couple of things that are important for this week. So this will be the first Thursday where you have a Thursday quiz. And I wanted to go over the purpose of that quiz is really to be able to develop skills that are a foundation for using biology to solve problems. So we develop our chemistry skills so that we can have a greater understanding of biology so that we can approach and solve problems. We really use chemistry as a tool to understand biology. And so our task for this Thursday's quiz is going to be to identify and draw functional groups, to be able to label hybridization, and then to draw Lewis structures and to calculate formal charge. So some of these are already familiar to you. We're just going to add in the functional group piece. And the criteria, what I'm looking for from you, is this ability to have clear, legible drawings and explanations to make sure that your calculations are accurate and that you have complete responses to the prompts. So hopefully that gives you something to look forward to for this Thursday. As I promised, for today we're going to look at one of, I think, my favorite stories in chemistry. So I want you to close your eyes and imagine for a moment. It's 1940. The Nazis have taken Copenhagen and they are marching through the streets. And a physicist by the name of Niels Bohr has just hours, maybe only minutes, to make 2 gold Nobel Prize medals disappear. And what's interesting about this is the following. These are medals that are made of 23 karat gold. They're heavy, and because they're shiny and inscribed with the names of their recipients, it's hard to make them disappear. Now, the Nazis have declared that no gold shall leave Germany, but there are 2 Nobel laureates, one of Jewish descent and the other who, although German, was an opponent of the National Socialists, have sent their medals to Niels Bohr's Institute of Theoretical Physics for protection. Because of German law, their act is a capital offense, if someone can find evidence. Now, the evidence is sitting in Niels Bohr's office, and it's clearly inscribed with von Lau, for Max von Lau, the winner of the 1914 Prize for Physics, and Frank, for James Frank, the physics winner in 1925. Bohr had attracted and protected Jewish scientists for years, and now the Nazis, knowing this, have Bohr as a target. So when the Nazis came to Copenhagen, a Hungarian chemist named György de Havasi, he would one day win a Nobel Prize of his own, was working in Bohr's lab. He says, I suggested that we should bury the medals, but Bohr thought that the Germans would dig up the grounds, the garden, search everywhere in the building, that it was too dangerous to try and bury them. So I decided to dissolve it. Havasi thought about chemistry. Maybe he could make the medals disappear. While the Nazis marched on Copenhagen, I was busy dissolving von Lau's and James Frank's medals. Now, this is not an obvious solution since gold is a very stable element. It doesn't tarnish, it doesn't mix, it doesn't really dissolve in anything, except for one particular chemical emulsifier called aqua regia, or water of kings. It's a mixture of 3 parts hydrochloric acid and 1 part nitric acid. Dissolving gold is a slow business. In fact, nitric acid loosens the gold atoms, after which the hydrochloric acid can move in, and then the chloride ions surround and transform the gold. These 2 hulking gold medals took a fair bit of time. Can you imagine the agony, waiting, wondering whether or not the Germans were going to walk in when you were only halfway done? It must have been an excruciating afternoon. De Havasi in his autobiography says, because gold is exceedingly unreactive and difficult to dissolve, it was slow going. But as the minutes ticked down, both metals were reduced to a colorless solution that turned faintly peach and then bright orange. By the time the Nazis arrived, both awards had liquefied inside a flask that was then stashed on a high laboratory shelf. When the Nazis ransacked Bohr's Institute, they scoured the building for loot or evidence of wrongdoing, but left the beaker of orange aqua regia untouched. Havasi was forced to flee to Stockholm in 1943, but when he returned to his battered laboratory after VE Day, he found the innocuous beaker undisturbed on a shelf. Havasi did a remarkable thing. He reversed the chemistry and precipitated out the gold, and then, in January 1950, sent the raw metal back to the Swedish Academy in Stockholm. The Nobel Foundation then recast the prizes using the original gold and represented them to Mr. Lau and Mr. Frank in 1952. Niels Bohr also had a gold medal, but he put his up for auction on March 12, 1940 to raise money for Finnish relief. The winning bid was anonymous, but later Mr. Anonymous gave back Bohr's medal to the Danish Historical Museum, where it can be seen today. Now, I first heard this story from Sam Keen's book, The Disappearing Spoon, and Other True Tales of Madness, Love, and the History of the World from the Periodic Table of the Elements. If you're curious about more chemical stories, I would highly encourage you to check out that book. This one has always struck me because I think it takes incredible courage to be able to stand up, especially when there's the potential cost to oneself. And I think both von Lau and Frank and Niels Bohr and de Hevesy did just that. So in my mind, they're chemical heroes. But the reason why this story is poignant for today is because we're going to be looking at acid and base equilibrium. So our purpose is to understand why products form in a reaction. So for example, why do proteins create molecules from substrates? And our task is to be able to determine the direction of equilibrium. And the criteria that we're going to use for this task is we're going to assign the acid and base using pKa, and then we're going to assign the conjugate base and conjugate acid. We're going to draw the mechanism, and then we're going to predict the direction of equilibrium. So equilibrium in the following acid-base reaction is going to lie to the right, on the side of the weaker acid and the weaker base. So if we think about that, we have two chemical components, acetic acid and ammonia on the left-hand side, and then our acetate ion and ammonium ion on the right-hand side. And if we do a comparison, looking at the pKa, pKa of 4.76 is lower than a pKa of 9.24. So acetic acid is the stronger of the two acids. So when we label then our equilibrium, we're going to label our acetic acid as the stronger acid, our acetate ion as the conjugate base. Our ammonia is the stronger base, which means it becomes our conjugate acid. So take a moment and describe the process of determining the direction of equilibrium. What assumptions do you make? What steps did you take? And what conclusions did you form? So think about, what do you have to know? What do you do with what you know? And then how do you make decisions? This is actually very similar to detect, elect, and connect. And of course, press pause if you need to, or you would like a little bit more time. If we take a look at acid-base equilibrium, we have one conjugate pair that's shown here in red, and we have another conjugate pair that's shown in blue. What do you notice? Well, in this case, the conjugate pair in red starts out as an acid HA, and when it loses the hydrogen, it becomes A-, the conjugate base. The other conjugate pair is water and H3O+. In this case, this is a base because it gains a proton to form H3O+. So notice, right, in this instance, water functions as a base. In the second example, where we have one conjugate pair, where NH3 gains a proton, so this must be the base because it's gaining a proton to become NH4 plus the conjugate acid, which means that water, because it's losing a proton to become hydroxide, must be the acid. So the acid loses a proton to become a base. So notice, water, if it loses a proton, is going to act as an acid, in which case it forms hydroxide. If water accepts a proton and is acting as a base, then it becomes H3O+. One of the things that you'll notice is that this concentration of H3O+ is what we use to define whether or not we have an acidic solution. So if I were to take the negative log of the concentration of H3O+, that would be my pH of the solution. And so if I have a significant concentration of H3O+, then I have an acidic solution. Once I approach 1 times 10 to the negative 7th, That's going to be a neutral solution because notice I have 1 times 10 to the 7th of my acid and 1 times 10 to the 7th of my base. And then as my concentration of acid diminishes further, I begin to become basic as a solution. Now, one of the challenges that we're often going to see when we're looking at acid-base equilibrium is whether or not our reaction is going to be reversible or irreversible. So the next question we're going to ask is, when does a reaction become irreversible? So if I take a look at this example, I have HCl, I have NaOH, and that's going to react to form water and NaCl. Now, because HCl is a strong acid, it has a pKa of -8, and water, my product, is a weak acid, that's a pKa of 15.7, there's a huge difference in pKa, roughly 24 pKa units. So the acid-base reaction then is favored by a factor of 10 to the 24th. So essentially, it's irreversible. So whenever I mix these two together, I'm always going to predominantly form water and NaCl, and it's going to drive to the right. I have very little of water and NaCl, if any, that recombine to form HCl and NaOH. So that's what we mean by essentially irreversible. Let's look at another example. By comparison, if I have methanol, which has a pKa of 15.2, and water, which has a pKa of 15.7, where now the difference is roughly 0.5 pKa units, this is what we would refer to as a reversible reaction. So at equal concentrations, the equilibrium favors the weaker acid and base by a factor of 10 to the 0.5, or 3.16. So my equilibrium mixture contains a 3.16 to 1 ratio of methoxide to hydroxide. So I have approximately 75% methoxide to 25% hydroxide. So both of these components are present in a solution at equilibrium, which means that I shuttle back and forth, where I have a slight preference for these products because my methanol has a slightly lower pKa than water. So when does a reaction become irreversible? There's really no hard and fast rule, but for practical purposes, a good rule of thumb is about 10 pKa units. So if there's a difference of 10 pKa units, then I can expect that it's going to behave like an irreversible reaction. Now, you are already familiar with how to calculate pH. That's the negative log base 10 of the concentration of H3O+, or the concentration in moles per liter. Notice that's going to be similar to the way that we calculate pKw. So in this case, pKw is the negative log of Kw. Kw, if you recall, is the concentration of H3O+ times the concentration of hydroxide, which I can resolve to the log base 10 of H3O+ plus the log base 10 of the concentration of hydroxide, which becomes pH plus pOH. So if I want to know what pKw is, that value should sum to pH plus pOH. And if you're wondering how we get to that, that's because we're really using our equilibrium value. So this is the concentration of our products in this case, divided by our reagents, and we exclude water because it's a pure liquid. So let's take that and practice for a moment. If an acid has an H+ concentration of 0.0001 molar, find the pH. So in order to do that, you're going to convert the number to the exponential notation. You're going to find the log and then solve the pH equation. So take a moment and do that calculation just to check to make sure that you and your calculator are on the same page. So what is the pKa of acetic acid if the Ka is 1.78 times 10 to the -5th? And then calculate the value of the ionization constant for the ammonium ion Ka if the pKa is 9.74. So take a moment, check your answers, make sure that you're comfortable doing this calculation because you will have to do so on a quiz in the not so distant future. So we know that pKa and pH are related concepts. pKa is the property of a compound that tells us how acidic it is. The lower the pKa, the stronger the acid. So take a moment and describe pKa in your own words. And again, press pause if you need a little bit more time. pH is a property of a particular solution that depends on the concentrations and identities of the components. Based on the relationship between the pKa of a compound and the pH of a solution, we can then predict whether a compound will be protonated or deprotonated. So if you think about pH, you should always be thinking about concentration, and specifically, you should be thinking about the concentration of the acid. So if I build my knowledge and my conceptual understanding, I know that pKa and pH are related concepts. The pKa is a property of a compound that tells us how acidic it is. The lower the pKa, the stronger the acid. I know that pH is a property of a particular solution that depends on the concentrations and identities of the components. Based on the relationship between pKa of a compound and the pH of a solution, we can predict whether a compound will be protonated or deprotonated. If the pH is lower than the pKa, then the compound will be deprotonated. If the pH is higher than the pKa, oh, sorry, I think I said that wrong. Let's double check. If the pH is lower than the pKa, then the compound will be protonated. If the pH is higher than the pKa, then the compound will be deprotonated. And if saying that gets confusing because of protonated or deprotonated, then think of a visualization that will help you make sense of that. So think of pKa as proton binding affinity. If a molecule has a low pKa, then it has low affinity for binding protons. Thus, it binds them weakly and it gives them up easily. This is a strong acid. So take a moment and convince yourself or your neighbor that you know the difference between pH and pKa. Using your pKa table that you've been given in class, you're going to solve these acid and base equilibrium problems. So because the pKa of acetic acid is approximately 5 and the pKa of NH4 is approximately 9, we know the equilibrium lies to the right. Because the pKa here is approximately 11, pKa of water is approximately 16, we know that equilibrium lies to the left. And here, because the pKa's are approximately equal, we know that our equilibrium will go in both directions. So if you think about patterns and how you can use patterns, one of the things that is useful is to have a range or an estimation of where you think a pKa might show up. So yes, you'll always have access to a pKa table, but it's useful to you to have a sense of what kinds of molecules have what kinds of pKa. So for example, alkanes always have pKa's of roughly 50. They do not want to give up their protons. If I think about hydrogen, H2, that has a pKa of 40. If I think of amines, that has a pKa of about 35. If I think of alcohols, that has a pKa of roughly about 16. And if I think about amine salts, they have pKa's of about 9. And if I think about halogenated compounds, so HF, HBr, HI, those are going to have pKa's that are much lower, 3 or below. Now, if we think about the way that structure and acidity interact, the most important factor in determining the relative acidity of an organic acid is the relative stability of the anion formed when the acid, HA, transfers a proton to a base. So there's a wonderful mnemonic I found that you can use to be able to remember this. It's credited to Dr. Christine Pruis, a senior lecturer at Arizona State University, Tempe, Arizona. So cardio, so charge, atom, resonance, dipole induction, orbitals, or cardio, are all of the factors that we think of when we're trying to determine, right, the relative stability of the anion or how acidic a compound is. So the electronegativity of the atom bearing the negative charge, so within a given period, the greater the electronegativity of the atom bearing the negative charge, the more strongly its electrons are held. The more strongly its electrons are held, then the more stable the anion A- is, and the more stable the anion A-, then the greater the acidity of the acid HA. So if we think about resonance delocalization of the charge on A, so if I compare the acidity of a carboxylic acid and an alcohol, both of which have hydroxide groups, then carboxylic acids are weak acids. They have values of pKa for most unsubstituted carboxylic acids. They're going to fall in the range of 4 to 5. So we know an example already, that's acetic acid. We also know that alcohols are very weak acids. The value of pKa for most alcohols falls in the range of 15 to 18. So how do we account for the fact that carboxylic acids are stronger acids than alcohols? Well, the reason for that is resonance. I can draw resonance for a carboxylic acid. I cannot draw resonance for an alcohol. So choose one anion and draw the resonance structure. Then choose the second anion and try to draw resonance. Why can't you draw resonance for an alkoxide ion? Why can you draw resonance for the carboxylate anion? The greater the resonance stabilization of the anion, the more acidic the compound. So there is no resonance stabilization in an alkoxide anion. We can write two equivalent contributing structures for the carboxylate anion. The negative charge is spread evenly over the two oxygen atoms. So that's the reason why the carboxylate anion contributes to greater stability, the ability to draw resonance. When we're thinking about structure and acidity, we also have to consider inductive polarization of the electron density. That's transmitted through covalent bonds caused by a nearby atom of higher electronegativity. So if I take a look at acetic acid with a pKa of 4.76 versus trifluoroacetic acid with a pKa of 0.23, it's the partial negative charges on the fluorine that lower the pKa of trifluoroacetic acid. Why does the pKa decrease from left to right? Can you provide evidence for the inductive effect? Again, if you need to, take a moment, pause, think about how you could frame your evidence in order to be able to support your claim. The more stable the anion, the greater the acidity of the acid HA. So if we think about structure and acidity, the larger the volume over which the charge on an anion or cation is delocalized, the greater the stability of the anion, or in this case, cation. When we're considering the relative acidities of the hydrogen halides, HI, HBr, HCl, HF, we need to consider the relative stabilities of the halide ions. So for main group elements, the atomic radii increase going down a group and increase going across a period. So what is the pattern? What changes from left to right? What changes from top to bottom? Take a moment and think about your argument. In the image shown here, the relative sizes of the atoms and anions. The neutral atoms are colored gray, the cations are red, the anions are blue. So anions are always larger than the atoms from which they are derived. For anions, nuclear charge is unchanged, but the added electrons will introduce new repulsions and the electron clouds will swell. Thus, HI is the strongest acid because the negative charge on the iodide ion is delocalized over a larger volume than the negative charge on chloride. The result of both resonance and the inductive effect is due to the delocalization of charge. If we think about Lewis acids and Lewis bases, any molecule or anion that can form a new covalent bond by accepting a pair of electrons is a Lewis acid. Any molecule or ion that can form a new covalent bond by donating a pair of electrons is a Lewis base. So, take a moment. What is the Lewis acid? What is the Lewis base in this reaction? When HCl dissolves in water, the strongest available Lewis base is the water molecule, and the following proton transfer reaction takes place. In this case, what is the Lewis acid? Methanol is the Lewis base, which means that HCl is my Lewis acid, and I form an oxonium ion. So when HCl dissolves in methanol, the strongest available Lewis base is a methanol molecule, and the following proton reaction transfer takes place. If we think about Lewis acids and bases, our halide ions are very weak. Our water, alcohols, and ethers are weak. Our ammonia and amines are strong. Our hydroxide ion, our alkoxide ions are stronger. And our amide ions are very strong. Lewis bases. Notice, what do they all have in common? Lone pair, and potentially, for the stronger or very strong, negative charge. Another type of Lewis acid we will encounter in later chapters is an organic cation, in which a carbon is bound to only 3 atoms and bears a positive formal charge. Such carbon cations are called carbocations. We're going to explore these in a little bit more depth in the week to come. For now, here's your big ideas with regard to acids and bases. We initially talked about Arrhenius. Then we talked about Bronsted-Lowry. And then we talked about Lewis. So Arrhenius describes H+ ions in solution and OH- ions in solution. Bronsted-Lowry describes H+ donors and H+ acceptors. Lewis describes electron pair acceptors or electron pair donors. And now you should start to have a sense of a relative scale of what is a strong acid, what is a weak acid, and what is a strong base, what is a weak base. Next time, we're going to be talking about alkanes, alkenes, conformations, conflagrations, and Newman structures. Thanks again. Have a great day.